Dr. Lyra Wang will talk to us now about the Appalachian Methane Initiative, developing measurement-informed inventories using multi-scale measurements. And frankly, this is some of the work that makes Arvind and I have a difficult time talking about logistics, because then we just keep pivoting to science. So I'm sure you all will be very excited to hear about it too.
Hi everyone, I'm Lyra. If you were at the workshop yesterday, I gave like a more technical version of this presentation. Hopefully today we're gonna convince you to work with us by me giving this shorter version again. So today I'm presenting a model that we built to develop facility level measurement informed inventory using multi-scale measurements. This is a work done by a group of scientists at MDAL as well as the project management team from SLR. So new policy and voluntary initiatives require accurate emission estimate at different spatial scales. We've heard a lot today about the Inflation Reduction Act as well as the newly updated GHGRP subpart W rules. Both require accurate accounting of facility level emissions estimates. While the scientists in this room will tell you that there are several challenges to estimate emissions at facility level. One of it is that emissions exhibit significant spatial and temporal variations from hours to days. So the graph you're seeing here is a recent study done by researchers at MDAL. The x-axis is the GHGRP-based facility level inventory provided by operators, and the y-axis is full facility Bridger measurement. So the diagonal line is the 1-to-1 ratio. So the closer the data points are to the diagonal line, the more aligned are the inventory as well as the Bridger measurements. So data points here represents facilities from 3 different US oil and gas producing basins. We see that snapshot measurements can be either higher or lower than the inventory for even the same facility, depending on when the measurement took place. And the facilities operated by the same operator could also have very different emission profiles. So the current GHGRP, or the conventional GHGRP way of calculating emissions or inventories, is to multiply emission factors and activity factors at the annual scale, which fails to capture this level of variation we observe through measurement studies. So in recent years, we've seen substantial advances from detection technologies, which enables methane emission measurement at various spatial and temporal scales. These technologies are continuous emission monitoring systems, aerial detections, and satellite detection technologies. They improved our understanding of emission variations, and there has been multiple measurement campaigns done to understand or establish emissions distribution at facility, regional, or equipment level. However, one common thing that we found throughout these measurement studies is that measured emissions, there's a gap between measured emissions and inventory estimates. And there are multiple reasons why this happens. One of it is that the inventory is developed on an annual scale. However, these snapshot measurements, they give you or they provide an estimate of emissions for one point in time. So the question really goes to how can we use measurement data to inform or develop inventory at the facility level? And we're, with my fantastic icons, we're gonna walk you through a typical data management process from the operator's perspective. So let's say an operator contracted a detection technology to conduct quarterly measurements for all of the facilities. So in this case, we assume this technology is an aerial-based technology. The company went out to measure all of the emissions on the facilities, and within a week or two, submitted data to operators. Then operator proceeded to investigate, okay, what are the emissions that are measured on the facilities? This could be you going into your internal data management system, or you can send a crew into the field to see what is being measured or what was measured. And anything that is identified as a fugitive emission will be repaired. Well, in that case, emissions from that one point in time, or fugitive emissions from that one point in time, is repaired. But can we tell how much methane was emitted in between these surveys? We've seen that emissions are very significantly throughout time, so we can't take snapshot measurements as inventory directly. So in that case, we'll need to build statistical models to understand how much methane was emitted. And here we're presenting that model. So this is the measurement-informed inventory model. It is a tool to develop annualized facility-level methane emissions inventory based on measurement data. So there are three groups of emissions this model takes into consideration. The first one is the measured emissions, which is very straightforward. This is the emission detected by the technology. And there are also emissions that are not detected by the technology. There could be two reasons for that. One is that emission did not happen during the time of measurement. In that case, we'll account for them in the one-time emission event emission. And also it could be that the emissions are too small for the detection technology to see. So in that case, we account for them in the below detection limit emissions. So today we present the basin MI model, which uses measurement data and basin-specific parameters to estimate emissions at facility level. We're also gonna incorporate the operator data into the basin MI model to show you how having the operational information would help us refine the model and provide more accurate emission estimates. Okay, so now we will demonstrate how to use the MI model to estimate facility-level inventories with measurement data from a large-scale aerial survey conducted by Bridger in Marcellus. So Bridger measured around 500 oil and gas production facilities in Marcellus just this past summer. And Facility A, which is one of those facilities that got measured, will be our case study for today. So using the basin MI model, we will develop a 90-day measurement-informed inventory for Facility A, which will include equipment-level emissions simulated from measurement data, as well as unmeasured emissions. And we'll then incorporate operator data to provide more accurate estimates. So let's look at Facility A. Facility A has 3 wells, 6 separators, and 3 tanks. When Bridger measured Facility A, there was 1 tank emission detected at 761 scuff per hour. Without knowing anything about emission intermittency, that translates into 31.6 metric ton for 90 days. To develop facility-level inventory, we first input all the measurement data into the basin MI model and start with the measured emissions inventory. Emissions are accounted for in the model by the different equipment groups on the facility. When we think about how much methane is being emitted, there are really 3 parts to it. First of all is what is the rate the source is emitting at? So that would be the emission rate. And then how long did this emission last? So that would be the duration of the emission. Then how often does this emission happen? So that would be like the frequency of it. When you multiply rate, duration, and frequency together, you have how much emission was emitted from this emission source. So for this measurement campaign, Bridger not only attributed the emission to the source equipment on the facility, but also did a count of major equipment groups on the facility. With that, we're able to develop equipment-level measured emissions distribution and multiply that by duration and frequency estimation developed from these measurement data. And then the model accounts for liquid unloading for one-time events, and we assume that liquid unloading are conducted without plunger lift, and it is simulated with the JGI data. For below detection limit, the model includes emissions from pneumatics as well as equipment leaks, and these are simulated with emission and activity factors from the GGRP data. So let's get back to Facility A. After inputting the measurement data into the basin MI model, Facility A is estimated to have 1.5 metric ton emission from separators and 0.1 metric ton emission from wells. The estimated emission from tanks is at 0.8, which is around 97% lower than the simple extrapolation of snapshot measurements. This is because that we take into consideration all measured emission rate on tanks, as well as the duration and frequency of tank emissions from all of the measured facilities. So for separator and wells, even though there's no emission measured during the time of measurement, that doesn't necessarily mean that over the 90 days, no emission happened on them. So the model simulates from known emission distributions and frequencies and durations and produces inventory estimates for those equipments as well. So with the assumptions listed before, we simulated one-time event emission at 0.3 metric ton, and below detection limit emission is simulated at 1.6 metric ton. So the total facility level inventory from basin MI model is at 4.3 metric ton. So let's take a minute to compare these two scenarios. When we're only looking at one snapshot measurement from facility A, we're not able to properly extrapolate that into a facility level inventory. However, the MI model accounts for emissions intermittency as well as unmeasured emissions and could give us a more reliable estimate for facility A. Okay, so let's see how operator data could change the measurement-informed inventory in this case. In general, operator data would help us understand the operational characteristics as well as operational events happening on a facility. So we collected the following data for facilities. Number one is the measured emission data from operator-managed facilities. So these would be a subset of that 500 that we measured. And then we collect data on root cause analysis, any controlled and uncontrolled tanks identification. We collect data on the exact count and type of pneumatic controllers on the facility, any recent outdoor surveys, and how is the liquid unloading conducted, or any one-time event during the 90-day period that we're simulating it for. So let's see how measurement-informed inventory changed in this case. So for facility A, the Monte Carlo simulation for separator, tank, and well are conducted with distributions from operator-specific facilities. In that case, the separator reduced from 1.5 to 0.7 metric ton, and the well stays similar at 0.1 metric ton. For tank emissions, all of the tanks on these facilities are uncontrolled tanks, so they're simulated with distributions from uncontrolled tanks. In that case, tank emission actually increased from 0.8 metric ton to 1.8 metric ton. So with operator data, the total equipment level emissions increased from 2.4 to 2.6. And from operator data, we know that liquid unloading is conducted with plunger lift that refined the one-time event emission to below 0.1 metric ton, and then there's no natural gas-driven pneumatic controllers on the facility, so that also refines the below detection limit emissions to 0.1 metric ton. So looking at these three different scenarios, snapshot measurement on facility A should not be treated as inventory directly because it does not account for emissions intermittency or any known unmeasured emissions. The basin MI model took into consideration the emission distributions from measurement data of the 500 populations and unmeasured emissions and estimated facility level to be 4.3 metric ton. And with the operator data, we're able to further refine that and provide a more accurate estimate at 2.7 metric ton. So in this presentation, we showcase the measurement-informed inventory model and how it provides a solution to estimate facility-level inventory with snapshot measurement data. The basin MI model will be published in peer-reviewed journals, and the goal for this model is for operators to take it and input the measurement data and generate facility-level inventory estimate from it. Moreover, we also demonstrate the importance of having operator data to produce more accurate emission estimations. With operator data, we can build operator-specific MI model that will reflect the operational characteristics in the inventory of facility level. Future versions of this model will include other technologies such as continuous emission monitoring and satellite detection technologies. So thank you for your time. If you have questions, feel free to ask them now or contact our team. Thank you.